We're in the final stretch of AP Calculus AB. Woo! All right. We have 5 weeks until the test. So what we're doing for these next 2 units are just reviewing integration, how to do it, how to spot different types of integration so that we know what to integrate when. All right. So above these problems in your textbook, there is some actual information that you should actually read, because we should actually read our textbooks, right? So read that information and figure out a plan to make sure that you're comfortable with integration. There is a formula sheet on page, I think it says 206, 211, something like that. It's somewhere around there. There's a formula sheet of the different integration things. So if you memorize a couple a day or work on a couple of them at a time, you will get very good at this. So what we're going to do now is we're going to look at some look-alike integrals and decide what we're supposed to do with them, because they each look very similar, but it turns out we integrate them very differently. So the first one, if we look at it, we have 1 plus x squared on the bottom and no x or anything on top. So it's just like a number on top, right? Anytime we have a number over something plus x squared, we automatically know this is an arctan form, because remember the arctan form looks like this with the number and something plus x squared. This one luckily doesn't actually even have to be manipulated at all, because the derivative of arctan is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared dx would be arctan x. So this one is just arctan x plus c. Okay, so the next one though, we don't have the x squared. So what do we do now? Well, the one thing I want you to remember is we can split a numerator, but we cannot split a denominator. So this one, we can't just split this into like 1 over 1 plus 1 over x. We can't do that. So this is 1 over some function, right? And this function doesn't have a power around it or anything like that. So we're going to actually use the U-substitution to do, because this is an ln form. Truly, you probably don't need to do U-substitution here, because you could maybe just recognize this, but you could, if you substitute 1 plus x for u, then du would be 1 dx. So we could just substitute in 1 over u du, right? And then what is the derivative, or the integral of 1 over u? Well, that's ln of absolute value of u plus c. And what was u? So that's ln absolute value of 1 plus x. Again, you probably didn't need to do a U-substitution here, because you can just see that this is 1 over some function of x. However, more often than not, you're going to have other ones that look like they might be ln's and aren't. So it's not a bad thing to do a U-substitution just to make sure that it actually works. Okay, so the next one, the first thing I see is I see a function and its derivative, which makes me believe that I'm probably going to do a U-substitution, because anytime I see a function and its derivative, that's a really big key for a U-substitution. So I have u equals 1 plus x squared. Therefore du equals 2x dx. Therefore dx equals du over 2x. All right, so now I know from looking at that that's going to do what I need it to do, right? So I have the integral of x du over u times 2x. The x's cancel out, and I put 1/2 on the outside of my integral times the integral of 1 over u du. And now I'm back exactly where I was in my last one, so now I have 1/2 ln absolute value of u plus c. And then I just have to substitute back in what my u was, which was 1 plus x squared plus c. So there we go. Again, just a little U-substitution. It's going to help me get that. Okay. Last one that looks alike. This one is tricky because everyone thinks, oh, this is something over some function. This must be an ln issue. But remember, this whole thing is squared. This whole thing is squared, and so this is probably not going to be an ln. So let's just take a look. We're going to do a U-substitution again. So let's just do u equals 1 plus x du equals 1 dx. Therefore dx equals du. So I can just substitute in. I have 1 over u squared du. And so let's rewrite this as u to the negative 2 du. Because remember, the integral of 1 over u squared is not the ln of u squared, right? Because that's not what it is. It's only if it was 1 over u, right? Just 1 over u. This we can integrate with just a simple power rule. This is just a power rule. Okay, so what do? We add 1 to the exponent, so that becomes negative 1, and then we divide by that exponent and plus c. And so now we're going to replace the u. We're going to substitute back in what we had, so we have 1 plus x times negative 1 plus c. We could distribute that out, so it's like negative 1 minus x plus c, or something of that sort, but there you go. Except what did I forget? I need a negative 1. Let's just undo that. I completely forgot my negative 1. I was just about to move on and went, that's not right. Okay, negative 1 plus x to the negative 1 plus c. There we go. So, we're done there. You could rewrite it if you wanted, negative 1 over 1 plus x plus c. Something like that if you wanted, but you don't have to. Okay. Next, these two are lookalikes as well, so we're going to integrate these. Anytime I see an ln in a function, I just assume that it's going to be my u. Sorry, I shouldn't say in a function, in an integral, because I don't know how to integrate ln. And so I've got to get that ln out of my integral so that I can now integrate what I've got left. So again, anytime I see ln in my integral, I'm going to try to do a U-substitution. So let's see. Here we have u equals ln x, therefore du equals 1 over x dx, therefore dx equals x du. So I can now do my substitution, and I have, instead of dx, I have x du over x times u. The x's cancel out, and I just get 1 over u du, which I know how to integrate, which is ln of absolute value of u plus c. And then I substitute my ln back in for u, so now I have ln of absolute value of ln of x plus c. So I have ln of ln. Okay, now this time, again, I'm going to just substitute in, or I'm going to do a U-substitution for ln, because I don't know how to integrate ln. I don't have like a formula for that. Okay, so u equals ln x, therefore du equals 1 over x dx. Therefore, dx equals x du. Okay, so I put this in. I've got u x du over x. The x's cancel out, and I have the integral of u du. And what is the integral of u? Well, it's u squared over 2, right? Because I just add 1 plus c. So now I have ln of x squared. We'll just say times 1/2 plus c. There you go. Okay, a lot of times, though, your integral is going to be in a way that you don't know how to integrate it with U-substitution, you don't know how to integrate it with ln or any of that kind of stuff, and we have to do a little bit of actual algebra first to get it in a way that we can do that. So, a lot of times you can multiply, so if it's like something squared, very, very often you're going to end up just squaring it. Like, don't do something to the 6th, right? If it's like 1 plus x to the 6th, don't multiply that out. There's got to be a better way, right? They're not going to give you one usually that you have to multiply out like that. But if it's like squared, there's a lot of times you're just going to have to multiply. Term by term division, remember, if there is a monomial on the bottom, meaning one term, then a lot of times we can just split it so that we keep the denominator intact. We always keep the denominator intact, and we split the numerator, so this one and this one, right? You'll see an example of that. Because if you remember, what is like 3/5 plus 7/5 is the same as 3 plus 7 over 5, right? If the denominator stays intact, I can combine or split either way, right? As long as the denominator stays the same. So that's what we're going to do if this was like x and this was ln of x plus, x to the negative 52. Something like that. We can put them together and take them apart. Okay. Long division is another technique because when the degree of the numerator is equal to or greater than the degree of the denominator, we're going to have to use long division because we can't use U-substitution because we would not be canceling out the right stuff, right? And then splitting and separating the numerator. All right, and we're going to have some more complicated ones in 9-7. Don't freak out. I know you're all freaking out, so stop. Okay. So here's one that we know we can't do U-substitution with because the inside, here's like a function inside. I don't see its derivative outside, right? I don't see its derivative anywhere, so I can't do a U-substitution here. So, and I see that it's squared, which tells me I'm probably just going to have to use FOIL. So I'm just going to have to multiply this out. So this becomes the integral of e to the 2x minus 2 times e to the 2x minus 2 dx. And then when we multiply that out, we get e to the 4x minus 4 e to the 2x, because I have negative 2 of them and another negative 2 of them, plus 4 dx. Okay, so this is my whole integral. And then what I want to do is, now I'm just going to integrate it piece by piece, right? I have 3 different terms, and I know how to integrate this, and I know how to integrate this, and I know how to integrate this. So let's do each one separately. So I'm going to write this one, the integral of e to the 4x. So we're just going to do that. If I want to do this one, you might be able to do a quick U substitution in your head, but if not, u is going to equal 4x. Therefore, du equals 4 dx. Therefore, dx equals 1/4 du. So I can substitute that back in, and I have e to the u times 1/4 du. So my 1/4 comes outside, and what is the integral of e to the u du? Well, it's just e to the u du, or e to the u. So I have e to the u, and u is 4x. Okay, so this is the integral of the first term. Okay, then we're going to have the integral of negative 4 e to the 2x dx. Okay, again, we're going to have a little u substitution thing going on here. So we're going to have u equals 2x, therefore du equals 2 dx, therefore dx equals 1/2 du. And so I can just plug that back in, and I end up with the integral, we'll just take that negative 4 outside, e to the u times 1/2 du. So I'm going to take that 1/2 out, so I have negative 4 times 1/2, which is negative 2 times the integral of e to the u du. And then what is the integral of e to the u du? Well, it's just e to the u, so I have negative 2 e to the u, and u was 2x. Okay, so that's my second piece. And now my third piece is going to be, okay, my third piece is the integral of 4 dx. Can we do that? Yeah, it's 4x. All right. So my final answer is going to be 1/4 e to the 4x minus 2 e to the 2x plus 4x plus c. So I just did algebra, and then I integrated it pretty easily with a U substitution. All right, that's it for this video. I will come back for the next one.